In this video, I will be implementing finite difference time domain method, first in 1D free propagation, then we will add polarization, meaning material, and eventually we will do three-dimensional full-blown FDTD simulation, and we will be doing this with Matlab. So before we even go to anything special, let's just write some background code. So like we propagate the electromagnetic field for 1,000 steps, and then we have like, first we do one-dimensional, so let's say we have 100 points, and then we have some electric field and magnetic field, and then here we update we have some time step in our propagation, and we calculate time derivative of magnetic field, update magnetic field, and then we do the same for the electric field, and then we will have some spatial points, and we will plot these fields. So, and we have some grid spacing, and we have some set of grid points which grow from 0 to n-1, and then we multiply it with grid spacing to get the actual positions over here. And then one more thing, maybe we initialize the electric field with some Gaussian, so something like this. And the end result is this one, and now we just need to fill out the actual code. Okay, so what we're going to do is first implement free space Maxwell equations without any sources, so they are here, and then we are going to say that the everything is only function of z, meaning that they are constant in, with respect to x and y coordinates, so we have only z dependence. And then we choose a polarization, so the wave is propagating in z direction. We choose that the electric field is in x direction and magnetic field is in y direction. So notice that all of these are perpendicular, so z, x and y. And then from just how curl is defined and evaluating these, we find that only components which remain are these two. So these two are the ones we're gonna have to implement. And secondly, we notice that we want the time derivative, so we define these in shifted grids. So these like both depend on the with first order derivative from each other. So if we shift the electromagnetic grid with 1/2 step, well, 1/2 grid point, then we can then we need the curl of the magnetic field at 1/2 step. But if you define the magnetic field in full steps, then we can just take for example kth and k plus 1th magnetic field like done here, and evaluate the difference, and this is a central difference operator which is more accurate now for this +1/2. So this is the essentially the procedure. So it all comes from G grid. So eventually we're gonna have these displayed as such, but for now we have only Ex, which is shifted half in x direction, and Hy, which is defined here. Okay, so in order to do that, let's first let's for example, so this is the final equation. So let's define few finite difference operators. So one of the reasons, so I'm eventually going to do this with some, for example, parallel Python, but Matlab is just so easy to play with things. So what we're going to need is difference operators, both forward and backward difference. So these are gonna go like this. I will show you in a minute what these look like. So here's finite difference operator. I'll reduce the dimensionality temporarily so it's easier to see. So this operator takes two grid points and uses the forward difference. So this operator essentially, if you have something here, here's 1 and 2 grid point values, this matrix multiplies them, then essentially it evaluates them in the between points 1 and 2. So, and then another one is the same but in backwards. So for example here, this one evaluates derivative between grid points 1 and 2. So it's 1.5. So this is the essentially the idea. So we use this, one of these will be used in electromagnetic field and one in magnetic field. Electric field and magnetic field, and the end result will be as in the. So now we just we can just from here. So Ex is c squared, and then derivative of By. So actually I will explicitly mention these Ex and Eb's here, since otherwise it could be a little bit so d by dB by dt is minus electric field minus there's dF here, and then dEx dt is minus c squared and derivative of y is minus c squared, and then now we use the backward difference operator and then By, and that's it. We just need to define c is 1 in our units, and let's see. Nope. So this one needs to be column vector dp y dt. Okay, nothing happens. It's probably because of this. So let's put back the 100 grid points. And so what is the length? So I rename these dx by, and as I said, this grid is shifted, so I'm gonna actually have to shift it I'm not sure should it be shifted backwards or forwards, but we'll see. And now let's take it a little bit slower. So we start with this initial, and we see that this Gaussian wave packet, it composes of left and right propagating waves, and it will split into two Gaussians with half the intensity, and it will propagate until it hits this boundary, and then it will reflect from there. Okay, so that's that. And now I'm gonna make periodic boundary conditions. So if you look at this operator, df, well, let's again reduce the dimension. We see that if we want periodic boundary conditions, we would need to operate on a grid point, which here would be here in the matrix, which would be like here in when it multiplies. And we see that if you put this yellow here, then we have a periodic boundary condition. So let's try df n1 equals df1 2. Let's see if it will work out. Yes, okay. And then we do the same for this one. So this corner is missing blue. So we do db. I guess these are transposes of each other. So db. Okay. So that's that. And then now we should have periodic boundary conditions. So we can check that. So speed of light, the system length is 10 and speed of light is 1. So the wave should go to left and right and through the system and then meet at the center exactly in 10 time units. So we can actually just propagate it only for 10 time units and see what happens. So now they went through the boundary, and that's it. They're exact. Okay. So that was the first part, the easiest part. I think this should be like this. So there's something one should know about these grids, is that they are also temporally offset. So you can look leapfrog Verlet propagator, for example. So that's why they don't perfectly overlap, but the end result is okay. So one could actually do some nice interpolation, like splitting this propagator so they would be an equal time. I mean, technically I could try to do it, so I would essentially propagate by only half time step here, and then after evaluating the EX I would evaluate it another half time step. So now they should be on equal time and more overlapping with each other. So yes, now they are aligned almost exactly. But for practical purposes we don't need this kind of, the actual order of the propagation is the same. Let's try light speed 2. Oh, so the time step was not enough for that, so let's decrease the time step. And now we see that in the same time, the system can travel twice through this length of the unit cell. So, and we see that it's cancelled quite well. So there's some lesson to be learned here. So let me put the relatively steep Gaussian. So this one looks still okay. Let me reduce the width of the Gaussian even more. And we start to see this kind of very weird thing. Maybe we should also reduce time steps so that we don't. Yeah, that was partly time step problem, but now we see that we have essentially the Gaussian split into two, but we have this trailing thing. And you can see that there's dispersion, so there's actually photon is massless particle. It should have always speed of light, so there's something massive in our simulation here. So I think the easiest way to see that, and also to debug these things, is to actually calculate the propagator in frequency and k-space, reciprocal space. So I'm gonna add electric field 1 at grid point 1 and nothing else. And then I'm gonna collect some data. So I'm gonna collect this electric field into this array, like so. And maybe I'm not plotting every step so that it's a little bit faster. And when the data is collected, we can then Fourier transform this data. So we do. So let's look at the size of the data. Let's do more steps. So let's look at so here's space axis and time axis. So we can do Fourier transform the space and time axis, so we get energy and wave vector axes, and then we can plot this, and then I'm gonna change it so that we can actually make sense. So we are gonna look at the dispersion of our FDTD approximation. So we do so we don't need all the time data, so only okay, we are starting to see a dispersion curve, and maybe we just also flip it like this. Okay, and now it's upside down. Let's try. Okay, so this is the, so why don't I label the axis also? So this is the k vector of the photon, and this is omega, and then group velocity here is the speed of light, and there's no curvature, so it's massless particle. But then when we end up in the close to the Nyquist frequency of the grid, of course we cannot no longer evaluate the derivatives exactly. We see that this dispersion curve curves, and then we have negative mass. So effectively we also have like particles with negative mass in our simulation. So this is of course, then one needs to take this into account, that one only adds structure to the system which is in this region, because this is essentially just will yield wrong results. Okay, so I'm gonna do a new file, and then we are gonna discuss about the polarization before we go into 3D FDTD. So the first thing to consider is just that the polarization is modeled by spatially localized independent harmonic oscillators. So basic equation of motion for harmonic oscillator is something like this. You have like so mass oscillating, and then there's some nominal eigenfrequency of the oscillator. This is the restoring force, and then the point is that this charge or dipole will be accelerated by the electric field, and this will be the polarization. And then we can relatively easily generalize this to polarization density. So we replace this mass with some R dependence and rename X into polarity P. And we have this Newton equation of motion. And well, we can already now implement this. So before we even, so we define here also px, and then we also need a conjugate coordinate, so we will call it yx. So effectively px will be updated. I have these equations here. So px, this y, is just defined as the derivative of px. So of course dpx dt equals then y times dt, and then the other coordinate y, which is this is the acceleration, and then that's minus omega squared. And times px. And then we have some omega here. And then this one also has the electric field, so there's some rho. And then plus 1 over rho times Ex. So I will then, this one depends on Ex here, so I will put this update step there, and then this update step there. And then I can also now plot the polarization, so Px. And I guess I can also plot the acceleration of it. So I have coupled these oscillators to the electric field, but not yet the opposite. I'm calculating the dispersion. Perhaps we extend it back here, and then let's put the Gaussian back. Oops, did I remove the entire? I have to retype the Gaussian line. Okay, let's see. Okay, so I will scale down this a little bit, and then I will fix the y-axis. So, and I will actually make it very slow so we can actually take a look. I think it might be. I'm missing DTs here, so that's why it's escalating so quickly. So, okay, now there's no need to scale this down. A little bit faster. So now we can see that there's some electric field, and the system is beginning to respond to that. So y is accelerating that way, and that will also then bring the polarization up here. But I'm actually thinking that should we have I think I will just change the sign here. That's because it's easier to sort of, it's just a definition of the polarization, but now it's sort of, we can see that the polarization P opposes the electric field, and E plus P is the displacement field. And that's like, so that's where the macroscopic polarization lies in. So, okay, but now we have to dig a little bit deeper into the theory of Maxwell. So we need to go into the macroscopic equations. This is how I derived it. There's easier ways, but we defined H and D. And D is important here because we have no magnetic isotropies or anything like this. So we have just mu0. But the displacement field now will contain this polarization density and also the electric field, and the macroscopic Maxwell equations are these ones. Now, we substitute a little bit back. So we substitute for D to get the polarization here explicitly. And then we substitute back for B with this one. So we get this equation. So because we want to keep E and B as our simulation variables. And then I already did this, is that I split this equation of motion into two. And for the polarization, and now we can combine all of these. So this is just c squared, so an E and B so we have done already this. So now we see that we have minus 1 over epsilon 0 mu of y. So there was time derivative of the displacement field, so we ended up time derivative of the polarization, which is just y. So these signs we can, if we flip this sign, we need to flip this sign, but otherwise it's arbitrary. So what we're missing, let's define epsilon 0. So say epsilon 0 is 1, mu 0 is 1, and speed of light is 1 over square root of epsilon 0 times mu 0. And then when we update the electric field, here we see, say, minus mu times dt and 1 over epsilon 0. And then I flipped this sign, so I think I need to flip also this sign now. Let's see. And it's yx. Okay. At least it doesn't break immediately, so let's increase the time step a little bit. And it sort of seems to be stable. Okay, so I sort of, it looks like that it might have worked, but there's only one way to find out, and that's to look at the dispersion. So I enable this dispersion calculator, and we'll see what happened. So this is something, but let's increase the omega here to higher frequencies so it's easier to see. Okay, so what if I put in logarithm so that it's hard to see the mode here. There's of course, yeah, I mean, I'm also missing one important factor. It's we have to define some coupling parameters, so how strongly the electric field couples. So I just assumed that the acceleration is defined by electric field, but this don't leave any room for controlling the so we should have some, effectively it's this E here which defines the coupling strength. So I'm gonna add this kappa here. So now we have increased the coupling, and indeed we have. So effectively we have relatively basic stuff happening here. So we have the photon, and then we have the excitations of the individual material, and then we have like effectively this is already a polariton. So we have the avoided crossing, these modes strongly couple, and the crux of course is here that look at the derivative of this line, meaning at the slope. So what if I, for example, change kappa? So let's first put it to 0. So this line looks like that, and I will leave the mouse there, and then I will add kappa 1, kappa 5. You see that the slope is decreasing. So as I add more and more, so effectively we are reducing the speed of light, and I can make it more pronounced if I put it lower. So that's like the basic idea how dielectrics work. So now we can see that this slope is really low compared to the speed of light. Okay, so we can also do metals. So we just put omega 0. Now we should have a plasmon. So we see that we completely lose all modes below the plasmon frequency. So this is the plasmon frequency of the metal, and then it continues being a photon. So this is why metallic mirrors reflect when they're hit with photons which are less than their plasmon frequencies, because there's just no modes. So there's no modes to carry, so one cannot excite anything in this, and they have no option but to reflect back on the available modes propagating to the another direction. Okay, so that was the lesson of that. It's probably a good idea to check bulk plasmon dispersion. So this is what we obtained now. Okay, I think we want to do surface plasmon, and for surface plasmon we need three-dimensional things. So that's simple, but it requires some bookkeeping. So for simplicity, I'm gonna assume that all the axes are the same and all the grid points are the same and so on. For speed, we only do 10 grid points per dimension for now. And then we start by defining these operators here. And now these are one-dimensional, and we can also make one-dimensional identity operator, like so, and also maybe just one sparse matrix with nothing but zeros. And now we just need to make three-dimensional operators. So we need to make, for example, dx. And to do that, we use Kronecker product. So we operate, we do it like this. And now, effectively, this acts as an identity operator, but it sort of multiplies the df, or derivative operator operating on the x-axis on all the y and z axes. So you can, I suggest you work that out. I have some other videos where this is explained, but now we have three-dimensional derivative operators, and we need to distinguish between the forward and backward derivative operators here, like so. And then we're gonna need the Laplace. So we're gonna need the Laplace operator. So imagine how we define the electric field. So now electric field is three-dimensional n by n by n. And then we also need to have these electric fields like so. And now the total electric field, we actually put everything into a vector. So we have 3000 times 1 vector. So 1000 grid points for 10 cubed, and then 3 of these. And the good part of this is that now it's very easy to build these operators. So now we have to go to our, so this is why I put that there. So we want to have the Laplace operator operating in this E. So it's going to be a block matrix, and then we need to have 0. So let's build three-dimensional 0 also. So we just, for lack of better, that we just get a matrix full of zeros with same size. So that's Z3. And then we look at, so this is multiplying by component. And then it's with respect to z, so we do dfz here. And then that was minus, and then we do dfy. So to guide, I'm going to put the vector also here. So this matrix is multiplying a vector which look like this. So now we see that dfz operates on ey, so we have derivative of Ey with respect to dz and so on. So now I'm gonna just have to fill this out. So there's dfz here, and there's 0, and then there's d minus df minus dfx, and then this is 0, and then minus dfy, and then dfx. Okay, so now I have defined the number cross forward operator, and let's just also define the backwards operator. Oh, I did not do it, so I will just change these f's. Like so. Okay, so we have the electric field, and then we need the magnetic field. So and then we need the polarization density. Well, let's first do just the bare Maxwell, because there's also many places this can go wrong. So I should have saved that previous file. Well, so then suppose we want the Gaussian here. I think then we're going to need the grid. So we have to create some grid like so, so that we can assign the electric field now with the Gaussian. So, and let's not collect data for now. We don't yet care about the material. So we have E and B. So this is just dB dt. I'm gonna remove all of these ones. And also for now comment the polarization. Like so. And now we used to have df, because that used to symbolize the full curl operator, but now in 3 dimensions we have to actually use the full-blown curl operator. So we have forward difference, so we're gonna need this operator here, and then this operator is gonna operate on E, like so. And then we have the backward operator, which is gonna operate to B, and like so. So I think that's it. Now we should have implemented the most trivial FDTD in 3-dimensional space. So I'm gonna have to modify these things. So now we have to back convert. So E is just a flat vector which contains all the grids. So first we need to reshape it. So I think the dimensions are in this order, and now we can maybe try to plot like two-dimensional slice of this field of, say, into x direction. And maybe also for the electric field, for the magnetic field, and maybe we here want to do another polarization direction. So let's see if we get anything out. Nope. So nothing but zeros. So I'm setting this EX too late. So the actual vectors were set here. Okay, and it blew up completely. So let's check. Is it a time step issue? So, okay, first of all, let's put grid spacing to 1, because my Gaussian here was centered at 5, so we have our spaces from 1 to 5. So that's the Gaussian there, except that now this is completely gray. That's some Matlab bug. Let's try again. Okay, so that's the Gaussian I set up, and then there's gonna be some propagation. So let's see how it goes. So let's increase the time step a bit. So these go between about 1 and 2. It seems that the electric field is just increasing without limits. I think one of the minuses I might have left here was from the actual Matlab. So these are the real equations. So E should have minus, but there shouldn't be minus in this one. That was left from the how the curl worked. Okay, now we have a propagation. It's propagating outward as a ring. Okay, so let's try to increase a little bit the grid spacing, for example, to get finer resolution, and let's not plot so often because that's slow. We need to have more steps. Okay, so that's three-dimensional FDTD equations for you, roughly. So now the next thing is to add the polarization, but I think it's still useful to use this to analyze the dispersion. So again, I will remove this one and just calculate the propagator for EX. And then I need to gather some data with EX. So first I want to put EX. So I will convert EX into real space. Then I use Fourier transform to get the X component of it and Fourier transform it. And then I want to do, so this is some temporal variable, and then there's no propagation in X direction for X polarization, so I want to look at this, for example, in Y direction, like so. I can squeeze those singleton dimensions out, and then this is the data I need to gather now. So like so, and then I think this holds for the amount of data, and then when it's done, I have already Fourier transformed So I need to only Fourier transform axis to this data. And let's see, do we get a dispersion? So nope. And that's probably because so if data is sized like this, I have to say I don't completely follow, but let's so yeah, I'm padding it with 2 points. The dimension is specified like this. Okay, nothing happened. So let's open that. So data is just once, nothing but once. How can that be? So it's data just once. Wait, what? So now there's some trivial bug here, but so how come so the problem of data is that it's nonsense, and I'm trying to figure out why. So it's nothing but once. So maybe, what if I take another axis and there's something there? Yeah, okay, when the dispersion is coming out. I think I'm actually might be, the axis might not be like x, y, z, but they might be z, y, x. Okay, but I mean I'm using x and then it's either left here or here and then y. So things should be okay anyway. So let's see if we can just, for example, increase the time step. Yes, we could. And then we had to say that we don't want so much. Okay, now it starts to form. So now we have three-dimensional dispersion. Like so, and then okay, so that's the speed of the light, the slope there. Okay, now we're ready to add the polarization. So I mean this should be quite trivial. So let's try. How slow will this be? If we do a very fine grid. But let that run while we think about this. So this should not require any big changes since y and p are local, so these equations work as they were. And then this here also probably works as it was. So effectively, I think it should work out of the box. So let's see. Maybe I don't have time to wait for this, but I can anyway Fourier transform what we have. Yeah, I mean, more points, the dispersion is smoother. There's some ringing effect because the amount of time we propagated was so low. Okay, but let's move back to 20. Well, 40 probably could compromise. We could update this here so we can okay. So now we have polarizable medium. Let's not do at first. Let's do metal, but dielectric. And yeah, I guess it's probably wise to define these initial conditions as they were for. Yes, I mean, this is in vain, but it's like maybe formally correct to define the initial conditions before starting to propagate. So we can see that the dispersion is starting to formulate. So we have the photon, and then we have the excitation of the dielectric. And then effectively the speed of light should change if we add more coupling. So, but now the frequency of the dielectric is sort of huge compared to the, so let's reduce it a lot. And it seems that we got ourselves a metal since we lost the full photon. So let's reduce the coupling a lot. So now we don't, so here's the excitation. So it's a little bit hard to see, but let's increase the coupling, and maybe I also need to, so let's only look at the relevant part of the spectrum so it's easier to see. And so we see that this is relatively typical dispersion in dielectric. And of course, we can reduce it back to metal. So let's just put omega 0. The electrons will just accelerate forever without any restoring force. And now kappa and rho will just define our plasmon frequency. And we have a bulk plasmon dispersion now in 3D system. So that's ends that part, and I think the final what we will do today is to look at the surface plasmon polariton. So now my coupling here is non-spatial, uniform. So actually I have to make, for example, this kappa here, I have to make it into a spatially dependent thing. So kappa actually, I will define it to be 0 like so. And let's, for example, do a plate of metal. So we say that kappa from 1 to n minus 1, and then all others will equal to 1. And then omegas here can be all zeros. So now we should have a metallic plate. And let's actually define it like so, since we're kicking it at 1. Let's look, can we make some sense? Okay, well, probably it's wise to use the Gaussian now. So I will center the Gaussian to like top, somewhat top left. And let's see. So I guess this is the idea that I can locally, kappa could be a matrix, non-linear one also, but I'm gonna make it into a vector. I'm gonna just squeeze kappa into a vector here. And of course it will be a vector operating on all of these, so we could have like, so it multiplies the x, e, y, and e, z, so we could have kappa x, kappa y, and kappa z for non-isotropic media. So, okay, nothing sensible happened. I'm still having this one there. So how? Okay, well. Never mind. So now the Gaussian is there, and then we're supposed to have some metal, but I don't see any metals, but I'm not sure where did we put it, so it's probably useful to little bit look what we are plotting. So let's, for example, try something like this. Well, okay, the best idea probably is to look at the polarization. So let's first look at the polarization to try to find out these indices, how they work. So this is P. Okay, we see so that's the metal there. So this bottom here is the metal. Okay. And then we can also plot the electric field in the same settings. So can we do this dimension to 1? So we can see that the wave packet started there, started to polarize, and it goes into the bulk. So maybe we would like to increase the plasmon frequency. So let's increase kappa. So it should reflect. And now it starts to reflect. You see that the magnetic field, I think this was, no longer goes into there. And here you see surface plasmon polaritons forming on the surface.